Welcome back. In our next section, we'll look at some of the review exercises for Chapter 11 and a couple carefully selected items from exercise set E, which is what we will look at first. So now we're back to these problems from number E. Let's finish number 1. To recap, we obtained the percentage of women who were over 5 feet 8 inches by using the standard deviation method to figure out the standard score for women with a height of 68 inches. And once we have their standard score, which is a z-score, we could get the proportion of the distribution that would be above that z-score. It was about 2.5%. So in our next part, we're looking now at of the women who were married to men of height 6 feet, what percentage were over 5 feet 8 inches? So we want women over 68 inches. Oh, hold on. We need our I can't undo on this screen. Women over 68 inches, let's just say with husbands, who are 72 inches. Why did I choose this other phrasing? Just because it was more succinct. So our first step is to find out of men who are a height of 6 feet tall, what is the standard score for how many standard deviations above average is their height? So we need to basically convert the average height of husband to a z-score. So we've got a score 72 height minus a mean of 68 over our standard deviation of 2.7. And I'd really appreciate it if those of you out there could, at least some of you, try to do the calculations along to help us get through this a little quicker. 2.7. So now we've got, this is a z-score of 1.48. This is a multi-step problem, so we're just going to remember that this is 1.48 standard deviations above the average. So to get the score, so we know that their wives are above average too. Their wives' height are above average, and that their wives' height is about the wives' height, the predicted y, is going to be equal to r times the standard deviation. Just based on the men who have this height, what would their predicted wives' heights be? This is our end goal. Oh, I just need to do some more computation over here. So we want to get it's just so much easier for me to write in this view than in the other one. Oh, okay. Okay. So we've got our husband's standard score. Remember that we need R times the standard deviation or the standard score of our husband's. So we're going to take R times 1.48. R was 0.25 times 1.48. And this will tell us how many standard deviations above the mean we expect the wives to be. So this gives us 0.37 standard deviations above the mean. And this is the new average, quote unquote, the new average for the wives once we convert this back to a raw score. So 0.37 times our standard deviation is 2.5. And we expect our new average is equal to this number. $0.925, this product. Yep. Times, yeah, so it's 63.9 or 64 inches. Now let's think about getting our new standard deviation. The new standard deviation is equal to I'll switch colors here. That's the new SD is, again, the square root of 1 minus r squared times the standard deviation of y. We found this proof before, but just to work out I'll present the formula here and then we'll plug in the number since we did work out this earlier, times our standard deviation of y, remembering that wives are the y. When we do the math on this equation here, we end up with new standard deviation equal to 2.4. Okay? So now we've got our new average and our new standard deviation. Technically for wives again. Now we have the information we need to answer the question B. Of the women who were married to men of height 6 feet, what percentage were over 5 feet 8 inches? Well, based on a new average of 63 inches, which is approximately 5 feet 4 inches, or 5 feet 3.9 inches, we can use our new average to help us get this prediction. Oh, I'm getting us a little bit of extra space here. So now we're going to get the z-score for women over 5 feet, for women at 5 feet 8 inches based on our new average. So we've got 68, 5 feet 8 inches. We're using again this formula. Z equals x minus x bar over the standard deviation. Thus, 68 minus 63.9 divided by our new standard deviation of 2.4 is going to give us a z-score of 1.7. Now we can go to our z-table and see what percentage of the distribution is beyond a z-score of 1.7. So this gets back to stuff we did in chapter 5 where you say, okay, we've got this z-score, it's 1.7. What's the area beyond this? Because we want to know what percentage we're over 5 feet 8 inches. And it's going to be, if we look that up in the z-table, about 4%. And if you are having a little trouble with your z-table, in the table that I discussed in class and posted, which is under the resources section, this would be the column C. That's what this area is. It's column C for a z-score of 1.7. So, do we now feel good about problem 1? Computed the new average, we computed the new standard deviation, we used those to get our more precise prediction. Okay, good. Now, let's move on to number 3, and I'm going to put this on a new page for us because obviously we're going to need the space. All right, so now we've got the same study where now we've, based on the average height of men, we want to predict their average forearm length. And it's not surprising, there's a strong correlation between height of a person and their average forearm length. So let's look at what percentage of men have forearms which are 18 inches long to the nearest inch. Yes, of course. So in this case, we are, oh, I see why you found this one tricky. They did that weird thing somewhere in here. I remember where they predicted, yeah. Sorry. Here we go. I'm just looking at my notes. So to do this, we still are going to use our the similar methodology, but we are now, they're just made it a little tricky. I'm sorry, Stephen, I can't open the exam on Friday. I just cannot guarantee it's going to be ready and fully tested by then. Because I cut material that we are covering, I eliminated some material from the next week, in the next section. I have to revise our exam based on that. And I think all my seconds are scheduled basically between now and Friday. So sorry, back to the problem, but I did see your question there. So we're using a similar process, but they've worded this in a kind of a tricky way by saying that they're giving you the outcome. So, and it happens to be also the mean. So we just want to know, okay, based on, oops, hold on. Here we go. So we know our general prediction formula is essentially y equals mx plus a, essentially. And we're going to solve this a slightly different way, but I'm just highlighting for you that we're used to just predicting y based on other information. But now we're not quite going the other way, but we know we're just looking at a specific predicted value, like in the previous problem, and we want to know what percentage has that score. So we can solve this. It's very similar. The reason I went back is to help highlight that this is very similar to number 1A. What percentage of the women were over 5 feet 8 inches? Now they're just asking what percentage of men have forearms that are 18 inches, but this is still the outcome variable. So we can use our same method that we used before. We'll get the we actually solve that somewhere else. So remember in the previous time we did this problem, or this similar setup, we converted our score of interest to, we got its standard deviations above the mean. In this case, it's going to be 0. I mean, this problem is just going to follow the same process as the other one. You can see it's essentially the same. Do you still want to cover this one? Because it's really the same process, and I just want to make sure we get to other items too. Especially given that I already know I'm not on the exam going to ask you to use compute new averages and new standard deviations. The questions on this section are mostly conceptual, not mechanical. So the percentage of men that have forearms which are 18 inches long to the nearest inch. Well, before we were looking at the percentage that were over a certain point. This time I wish we, I'm assuming that because they say to the nearest inch that the 18 inches long is a range of scores from 17.5 to 18.5. Exactly, and since it's the average, we can just use the standard deviation for the average. And let's see. And if we get our 1 minus r squared value here, exactly, it would be around 34%. And it's just, it's kind of tricky just because they sometimes give you these examples of, it's not an extreme, but it's kind of an extreme because choosing the average means that the z-score is 0. So that's why I know the book says 38%. I'm trying to reconcile that. I don't have a quick answer for you. Why they have 34%, or why we have 34%, they have 38%. But I think that we are just spending, could we work this out? Sure. Could we work out a bunch of other problems in the same time to do this and be better prepared in the long term for the exam if we went with option 2? Option 2 is the one I'm recommending. So could we work this out? Yes, but I just don't think it's a good use of our time. I think we should move on. Thank you. Let's do options 2, because as I keep saying, it's not on the exam. And I'm not saying we should just do things that are on the exam, but I do try to make the exams represent the really important stuff, not the little minutia. If it's on an exam, it's something like that I see as a high level topic. So I promise you, if I say something's not, you're not going to be asked to do it on an exam, you won't. So yeah, let's just do these, move on. We've got the general method for getting the new standard deviation and the new average, and trust me, that's plenty. So looking at our first review item, that's what I'm saying, Sarah. I do agree. It seems like we're wasting a lot of time. That's why I keep saying I'd like to move on from this, but everybody's got more questions about this example. We're just going to move on. It hasn't been 2 hours. It's only been like 20 minutes, but it seems like a long time, doesn't it? Because really what we did during the first part of the lecture is all pretty essential. Remember, this was a question that was added in at the end. And I didn't really include the topic in the lecture. So I did include these items in the lecture because they are helpful and important for the exam. So looking at number 1 here, we've got the RMS error of the regression line for predicting y from x. And this should be pretty easy, but remember that we need to use the standard deviation of y, and we'll use our 1 minus r squared here. More information if you feel unclear about that, it's on page 186, but we did talk about this already a bit. Item 3 says Tuddenham and Snyder obtained the following results for 66 California boys at ages 6 and 18, and the scatter diagram is football shaped or heteroscedastic, and we want to find the RMS error for the regression prediction of height at 18 from height at 6. So average height at 6 is our predictor. And average height at 18 is our outcome, or predictor or outcome, or independent variable, dependent variable. Okay. And we want to just get our RMS error. Remember that the RMS error is equal to the square root of 1 minus r squared times the standard deviation of y. We just need to apply this formula here. So we've got the square root of 1 minus our r squared, r is 0.8, squared times our standard deviation for y is 2.5. So if you work this out, you'll see that it's going to be 1.5 inches. I'm sure you can confirm that yourself. So we know that the RMS error for the regression prediction is 1.5 inches. If we go the other way to get the RMS error for the regression prediction of height at 6 from height at 18, it makes less sense. The correlation is still the same though. And the formula is the same. Except we substitute in different values, of course. We've got now 1 minus r squared, still times our standard deviation of y, but we've now recast, we've switched these around. So now we're saying that average height at 18 is the predictor, and height at 6 is the outcome. So we get the square root of 1 minus r squared. Remember, that's still 0.8 squared times our standard deviation. Now y is average height at 6, so it's 1.7. And we'll end up with an RMS error of 1 inch. 1.02, yeah, approximately 1 inch. It's fine to round in this case. Yep. Okay, so see how we can use the RMS error for our regression predictions. Pretty simple to find. This you should be able to calculate. Yeah, you definitely should be able to find the RMS error, and it's a whole chapter in the book. Well, a statistical analysis was made of the midterm and final scores in a large course with these following results. And we'll assume again that they've got the X value on the top and the Y on the bottom when giving us the data. And it's normal and in keeping with important ideas. You want to make sure your regression makes sense. You would normally predict your final score from the midterm, not the other way. The scatter diagram was football shaped. For each student, the final score was predicted from the midterm score using the regression line. For about 1/3 of the students, the prediction for the final score was off by more than blank points, and we want to fill in the option here. So if we want to know approximately how much the prediction score would be off for about 1/3 of the students, we want to know what the RMS error for the prediction is. So we're going to use the same formula again. 1 minus r squared times the standard deviation of y is equal to then, it's the square root of 1 minus our r squared is 0.6 squared times the standard deviation of y is 15. And when you work this out, you get about 12. And so the prediction for the final score was off by more than 12 points. Now we need to predict the final score for a student whose midterm score was 80. Now we know that the midterm score of 80 is, we can convert this to a z-score again. I think you can still read it okay if I make these a little bit smaller. If there's a problem, let me know, but we just don't have enough space here. So now on B, we can predict the score for the student whose midterm score was 80. Well, we need to convert to a z-score first. Z equals x minus x bar over the standard deviation. So that's equal to, now we're looking at 80 minus the average midterm score of 50 over our standard deviation of 25. So what's this z-score? Well, the student is 1.2 standard deviations above the average. So if we want to get their score in the final, we know that they should be about the average on the final by R times 1.2. R times their z-score, which will be 0.6 times the z-score of 1.2. And that's approximately 0.72 standard deviations. And we can convert that to a raw score by just using, the inverse of this formula, which is equal to our x. Raw score is equal to the z-score times the standard deviation plus the mean. So our z-score is 0.72 times our standard deviation, which is 15 on the final, and the mean for the final, which is 55. Wait, that's not quite the, wait, 0.72. Yep, so they're about 10.8 points above the the mean, and that would be a score on the final of about 66 points, or precisely 65.8. There we go. Okay. And now, how much is that prediction likely to be off by? Well, this is going back to the same idea that we did in part A here. The RMS error is telling us the amount that the prediction is likely to be off by. So we're going to say 12 here because we already know that the RMS error is 12 per part A, right? Okay. And now we'll use the data in 4 to answer some more questions. What percentage of students scored over 80% over 80 points on the final? So we've got a percentage of, Stephanie, that it's, the error is 12 points. Actually, the student, in this previous example was above the mean. So they did better than the mean with an error of 12 points, which is a pretty big error. But they did better than average, which too bad. So what percentage of students scored over 80% on the final? Well, we're going to go back to remembering how to use the normal approximation within the regression. And so we can convert 80 to a standard score and then get the percentage in the distribution. We're going to need these data, the average final score. So we're using there's our data from exercise 4. I'll put it down here. What percentage of students scored over 80% on the final? Okay, well, the average final score of 80 we can get using that same method by converting 80 to a z-score. So that's going to be 80 minus our mean of 55 by a standard deviation of 15. And that'll give us a z-score of 1.67. And we can go to the z-table. Remember, at this point, you should be able to look at your z-table, find a z-score of 1.67, and then look at, in order to get the students who scored over 80, we want to, again, use column C. Oops. So here we have our z-score of 1.67, corresponding to a raw score of 80. And what percentage is this? This is going to be column C on your z-table, and it's equal to about 5%. Now we need to look next at the students who scored 80 on the midterm, and then find the percentage that scored over 80 on the final. So we can again get our new average and new standard deviation per our previous example. Let's see. So now we want to know how many standard deviations above the mean is, of the students who scored 80 on the midterm. So we'll get a new average for the students who scored above 80 on the midterm. And our new average is can be estimated by finding out how many standard deviations above the mean we are again. So 80 minus now 50, that's, of the students who scored 80 on the midterm. So we use our midterm score here. So that's 30 out of 30 is, we can get how many standard deviations above the mean this is. Again, we're just using the Z formula here. And the standard deviation, should be able to see that. So we've got then 30 over 25, and that's, I forgot to write that down earlier. 3 over 25, it's 1.2. So we're 1.2 standard deviations above the mean, and that tells us that our group is going to be above average on the final. And how much above the average will they be? We can take that by getting our R times our standard deviation we just found. R is 0.6 times 1.2. So we know there'll be 0.72 standard deviations above. We can just multiply by the size of the standard deviation on the final. Times our fifth standard deviation of 15. So we end up with Z, so our predicted size above the mean here, 0.72 times our 15 is 10.8 points. Above the mean on the final. So this is 10.8 points above the mean. We need to add this to our average final score. To get there, that would tell us their predicted score on the final based on students who scored 80 on the midterm. And to get the percentage above that, we already know the z-score here. It's going to be 0.72, so we can just look that up and get the, again, column C. And sorry, I don't have the Z table already open here on the computer, but I'm sure somebody out there has their Z table. It's probably approximately 50, 54, 80. So about 15%, give or take. How did I get that 15% give or take? I said, okay, I know that at a z-score of 1, there's a percentile rank of 50 plus 34 or 84%. 84 percentile, so that would be about 12 there. This is a little bit below 1, but I just approximated it because I don't have my Z table right in front of me. So I would say it'd be approximately 15%. That's fine for now. We did similar problems earlier. So I want to make sure we have time to look at the next topic. The freshmen at a large university are required to take a battery of aptitude tests. Students who score high on the mathematics test also tend to score high on the physics test. On both tests, the average score is 60. The SDs are the same too. The scatter diagram is football shaped. Of the students who scored about 75 on the mathematics test, we want to figure out about how many scored over 75 on the physics test. 75 on the math test is, well, we don't know exactly how many standard deviations, but the mean and standard deviation on both tests is the same. So of the students who scored about 75 on the mathematics test, we would assume that we've got just less than half scoring over 75 on the physics test. Why not just about half? Because they say there's a high correlation here, but we don't know exactly what it is. We just know that they are associated and there's a high association. Well, we know that option 3 is right because the regression effect predicts that there won't be a perfect association between these two, that there'll be even though it's a high association, it's not perfect. So we would have less than half at this same point. Okay, Stephanie, have a good night. Every year, baseball's major leagues honor their outstanding first-year players with the title Rookie of the Year. The overall batting average for the Rookies of the Year is around .29, far above the major league batting average of .26. However, Rookies of the Year didn't do so well in their second year. Their overall second season batting average is only .275. Baseball writers call this the sophomore slump, the idea being that star players get distracted by outside activities like product endorsements and television appearances. But does the data say that? I mean, do the data support the idea of the sophomore slump? Not really, because based on our knowledge of data, we would expect that this is just due to the regression effect. One of your exercises in the chapter, it goes over this idea of regression to the mean, or it's the example that is looking at predicting students, that students who do well on the pre-test tend to go down on the post-test. So does their teaching intervention make the students get worse? No, it doesn't, because we would just predict that the repeated testing would tend to see a regression to the mean. It's the regression effect. And that's what they want you to recognize here. There's a small decrease, and we would imagine it to be more due to the repeated measurement and the regression effect than necessarily these other outside things that are not quantified and that we don't have information about. And this is an important thing to keep in mind when you're thinking about what's going on in some data, because you can only really speak to what the data actually speak to. We don't know how distracted these rookies were by product endorsements. We don't have any kind of data on these. So it's really on a just an aside, but a really important one, is that you really cannot bring in these other variables and attribute a causal connection to them. So we have one final problem here. The figure below is a scatter plot of income against education for a representative sample of men aged 25 to 29 in Texas. Is something wrong? Well, what do you think? Does something seem odd about this graph? You might be wondering, why does it have the data in lines like that? That's not the problem. The lines are there because we have to figure out where the lines are there, because those are the specific points where they took the measurements. They took the measurements at, you know, they quantified this variable at 12. Oh, sorry, I'm pointing on my actual screen. So they measured 12, 13. They didn't have, it wasn't an option to say you had an educational level of like 12 and a half years. So you can, that's why we can see the values there. And there are some notable things, though, that are kind of strange on this diagram. There are a lot of people with 9, 13, and 7 years of education. So 9, 13, and 7 years of education, or 17, I'm sorry. But very few people with 8, 12, or 16 years of education. Notice that. Very few there, here, and 16. Oops, 16. And of course, there's nobody with 0, although 3 people somehow have 1 year of education. And that, based on this, we could see that it seems like a year was mistakenly added to the years of education, because we would expect there to be concentrations, concentrated points of data about educational levels that are more generally associated with standard educational levels that are seen. So 12 years of education, this is graduating high school. We would expect this line here to be 12. Very few, you know, it's much less common to, you know, graduate high school and then it's not like most everybody goes on and does 1 more year. Mostly there's this concentration here, which should really be at graduating high school. 16 is where we would see the other one, which is college. And so you can see that it seems like there's a little bit of shift. We even see some concentration here, which would be at 2 years of like an associate's degree, right? And so that's what, there is something wrong, which is that looks like everything was shifted just a little by 1 year. Well, I know this material is kind of tricky, and I want to make sure to that the take-home point here of all these review exercises is that you really want to know how to get your, in terms of for the exam, you'll want to know how to get your root mean square errors for predictions and the basic conceptual points here of the error predictions, which are, you know, things like the applying the normal distribution generally to the data, remembering that the difference between the actual value and the predicted value is a residual, and that's the prediction error. You should know the difference between a homoscedastic and a heteroscedastic diagram. What's the differences there? And when is it appropriate? You know, what's the meaning then? If you have you know, what changes if you have a heteroscedastic diagram, remembering then prediction errors are going to be different. And so these are some important takeaway points here. For prediction errors. So thank you for all your hard work tonight, and take a little break. Remember, for the most efficient way, do some statistics every day.